So today we're going to have a look at the January 2014 Physics Unit 2 paper from the WJEC with question number 1. This is about a transverse wave that's photographed against a background of lines, and these lines are 0.05 meters apart. We've got two photographs. One is taken at t equals 0 and the other at t equals 0.1 seconds. And a wave is moving from left to right. And the first part of the question is to work out the wavelength of the waves. Well, the wavelength of a wave is defined as the distance between two consecutive points along a wave that are in phase. For example, the peak A and the next peak along that I've marked with a circle. In between those two peaks we have 8 divisions, and 8 times 0.05 is 0.4 meters. To calculate the speed of the waves for the next part of the question, we have to make an assumption, and the assumption that we're going to make is that the wave has only moved one division to the right, so that the peak at A has basically moved there, rather than the possibility that it could have moved, for example, 9 divisions to the right. So let's write that assumption down. Then we can calculate the speed of the wave from speed equals distance over time. The distance travelled in between the two pictures is 0.05 meters, and the time taken is 0.1 seconds, so that gives us a speed of 0.5 meters per second. Next we're asked to calculate the frequency of the waves. So we can calculate the frequency of the waves simply from frequency is speed divided by wavelength. Speed of the waves 0.5, wavelength of the waves 0.4, gives us a frequency of 1.25 Hz. Next we have to compare the amplitudes of the wave at positions A and B along the string. And the key to this is the knowledge that progressive waves, every particle along the wave has the same amplitude, because the amplitude is the maximum displacement of any particle from its undisturbed or equilibrium position. Every particle won't be at the amplitude at exactly the same time, so here we quite often find that people think that A has a greater amplitude than B. But if you give the wave a few seconds, then both A and B will have passed from their equilibrium positions up by exactly the same amount, so their amplitudes are the same. The last part of the question asks us to compare the phase of the waves, and here a phasor diagram can be helpful. So if I number the spokes of this phasor diagram 1, 2, 3 and 4, and remember that it rotates anti-clockwise. If we refer to the first diagram, we see that A is at a peak, and therefore it is represented by phasor spoke 2. If we look at B in the first diagram, it's at its equilibrium position, but in the second diagram it's moved upwards a little bit. And the phasor spoke that starts at the equilibrium position and moves upwards is B. So it should be clear to see here that A is leading B by 90 degrees. Thank you very much for listening.